Welcome to While We Were Distracted, the podcast where we explore topics that often get overshadowed in the rush of daily life.
Okay, so let's unpack a belief that I think we all hold to be absolutely true. North is always north.
Right.
For centuries, that idea has been, the anchor for everything. Global navigation, map making, all of it.
And we should probably clarify which north we're talking about, because there's the geographic North Pole, which is that fixed point where the Earth's axis meets the surface.
That one's reliable.
That one stays put. It's very reliable.
But the point our compasses actually rely on, the magnetic North Pole, is, well, it's acting like a car running out of control on the Arctic ice.
That's a good way to put it.
It's accelerating, it's braking, and it's behaving in ways that scientists, according to the people who model this stuff, have just never seen before. It is, to put it simply, restless.
And what's so fascinating is that this restlessness isn't some, surface level thing. It's a direct, measurable reflection of what's happening deep inside our planet.
Absolutely. So our mission for this deep dive is to get into this dramatic and chaotic shift. We need to figure out what's driving the magnetic pole sprint toward Siberia, why it recently slowed down, and what it all means for, well, everything from global navigation to the northern lights.
To really get the motion, you have to understand the engine. And this whole system is powered by what we call the geodynamo.
Okay.
The magnetic field isn't like a permanent magnet just stuck inside the Earth. It's dynamically generated about 1,800 miles beneath our feet, in the outer core.
That's where all the magic happens.
It's pure physics, really. That outer core is this huge churning layer of incredibly hot molten iron and nickel.
Right.
And as that fluid moves, it creates these massive convection currents, which then generate electric currents. The whole thing acts like a giant self-sustaining planetary generator, the geodynamo.
And the movement of that fluid dictates how the pole wanders.
Precisely. If the fluid 1,800 miles down changes its flow, we see the magnetic pole change its speed and direction right up here on the surface.
So let's track the journey of this moving target. It was first located back in 1831, right? By the explorer James Clark Ross.
Yeah, way up in northern Canada on the Boothia Peninsula, a huge scientific discovery for its time.
And for over a century after that, its movement was pretty steady.
Remarkably so. It was this gentle, predictable wander. It drifted maybe 6.2 miles, about 10 kilometers, every year. Navigators could count on that.
But that gentle cruise, it ended pretty abruptly. Around the turn of the century, the acceleration was just immediate.
It was. The speed jumped dramatically, peaking in the 2000s at somewhere between 31 and 34 miles a year.
That's 5 times its historical speed.
It was moving so fast, it actually left Canadian shores completely by the year 2000. And its destination was clearly, Russia and Siberia.
And that must have been the moment that set off the first real alarm bells.
Absolutely. The models just weren't keeping up anymore.
So you'd think, okay, it's going to keep going at this new top speed.
Yeah.
But the core just threw everyone another curveball.
It slammed on the brakes. That's the most recent and honestly the most confusing part. In the last 5 years, its rate of movement slowed way down.
To what?
To about 22 miles, or 35 kilometers per year. And the geophysicists monitoring this confirmed, that this is the biggest drop in speed they have ever documented.
So a historic peak speed, then a historic slowdown. It really is chaotic.
It's not just moving, it's oscillating, it's shifting direction, it's defying the smooth models we use for prediction. This volatility really confirms that the forces governing the field are they're far more complicated than we thought.
Which brings up the question, if the core is so chaotic, why is the pole targeting Siberia so precisely? That sounds like more than just a random wander.
Right, feels directed.
It feels like a push or a pull.
And that's where the idea of localized field strength comes in. See, it's not just one big magnetic field. It's more like a collection of magnetic patches from different currents in the core.
Oh, okay.
Geophysicists like Sion Begin, they theorize the pole is basically caught in a planetary tug-of-war.
So who's winning this tug-of-war?
Well, in the current scenario, the field is getting much weaker underneath Canada. It's losing its pull.
Okay.
At the same time, the field is getting stronger around Siberia. So that combination creates this powerful magnetic attraction that is literally dragging the magnetic pole toward that Siberian strong spot.
Suddenly, the erratic movement feels completely rational. It's just chasing the strongest signal.
It is. And we have to put all of this in an even broader context. The Earth's magnetic field overall has gotten about 9% weaker over the last 2 centuries.
Wow.
Yeah, and that global weakening is a key piece of background information here. It hints at a potential instability that connects to some much bigger questions.
Which we'll get to. But
And
first, let's talk about the practical side. What does this mean for the people actually using this data? I mean, we're not talking about hikers.
No, we're talking about massive global infrastructure, the airline industry, shipping, military operations.
The stakes are immense, especially in the Arctic. Everyone uses GPS, but near the poles, GPS gets notoriously unreliable.
It does. It becomes erratic. And that forces pilots and navigators to fall back on magnetic heading data.
And that's where the World Magnetic Model, the WMM, comes in.
Correct. The WMM is the global map. It's a joint project between the British Geological Survey and NOAA, and it tries to predict the field's drift over 5-year periods. The whole goal is to prevent deadly navigational errors.
But the pole's crazy acceleration made the WMM obsolete almost overnight.
It created real-world errors, yeah.
Huh.
They gave this fantastic example to show just how serious it was. If you tried to navigate a long-haul flight, say from South Africa all the way to the UK,
Okay.
using an outdated WMM, the error from the shifting pole would leave you a staggering 93 miles off course by the end of your trip.
93 miles. That's the difference between landing at an airport and running out of fuel over the ocean.
It is. The chaotic core basically broke their 5-year planning window. The error built up so fast that in the late 2010s, they had to declare a navigational emergency.
An emergent.
Yes. They were forced to update the WMM a full year early in 2019 to prevent widespread errors for airlines and governments.
That must have been a huge technical headache, pushing emergency software updates across entire fleets of planes and ships.
A massive global coordination effort. And now, they've learned from that. The latest revision has some major tech upgrades. They've dramatically increased the spatial resolution of the map.
So they can see the magnetic landscape in much finer detail?
Exactly. About 9 times more accurately. This lets the WMM model those localized patches, like the one pulling the pole to Siberia, with far greater precision. It really helps specialized users, military advanced science.
But for my phone's GPS.
For general consumer GPS, the standard model is still the norm.
Got it. Now for the great cosmic question. Since the pole is moving so fast towards Siberia, will the northern lights, the aurora borealis, also shift?
That's the logical conclusion, isn't it?
I mean, are we going to see them less over Canada and the U.S. and more over Russia?
Well, the aurora exists because our magnetic field creates this protective net, the magnetosphere. It funnels charged particles from the sun into the polar regions, and that's what causes the light show.
So if the funnel moves, the lights should move.
It stands to reason. But here's the crucial distinction that recent studies found. It all depends on which north the aurora is actually following.
Okay, there's a catch.
There's a catch. We have to distinguish between 2 types of magnetic poles. First, you have the magnetic poles.
Right, the ones we've been talking
The
about.
ones we've been talking about. The physical point where a compass needle points straight down. They move erratically, they speed up, they slow down.
Okay, that's the messy reality. What's the other one?
The second kind are the geomagnetic poles. So imagine for a second that the Earth didn't have a chaotic core, but instead had a single perfect bar magnet stuck right through its center.
A nice, tidy bar magnet.
Exactly. The geomagnetic poles are the calculated endpoints of that imaginary, mathematically perfect magnet. They're an averaged out version of the field.
So the wobbly magnetic pole is the axis of a spinning top, but the geomagnetic pole is the perfect line drawn through its center.
That's a great analogy. And what scientists have found is that the aurora actually follows the path of the more stable, averaged-out geomagnetic poles.
Ah,
And since the geomagnetic pole is not moving anywhere near as fast as the erratic magnetic pole,
the northern lights are staying put.
the northern lights are staying where they are, at least for now. Good news for aurora hunters.
That is a wonderful piece of clarity. Okay, let's shift to the final and most dramatic implication. We said earlier the whole field has weakened by about 9% over 2 centuries. And that weakening is the signal that fuels the big discussion. Are we headed for a full geomagnetic reversal?
This is the biggest question of all. A geomagnetic reversal is exactly what it sounds like. North and south magnetic poles just swap places. A compass would point south.
How long would something like that take?
It's a vast geological process. It doesn't happen overnight or even in a lifetime. A full reversal can take thousands of years to complete, and the transition period, when the field is chaotic and weak, can last for tens of thousands of years.
It sounds catastrophic, but it is a natural process.
It's absolutely natural. They happen periodically, on average about once every million years or so, but the timing between them varies a lot.
And the last one was when?
The last time it truly flipped was about 750,000 to 780,000 years ago.
So based on that timing, are scientists sounding the alarm? Is this dramatic shift toward Siberia a definite sign that a flip is starting?
Scientists are very, very cautious about this. They are not predicting an imminent reversal. While the current movement is historically fast, we just don't understand the mechanism well enough to predict a full flip. This chaos doesn't automatically mean a reversal is beginning.
But if one were to start in the modern era, the impacts would be severe, mainly because the field gets so weak during the transition.
They would be. I mean, life has adapted to these flips for eons, but modern technology hasn't. You're talking about scrambling global navigation, severe disruption to radio communication, and a much higher risk to all of our orbiting satellites.
Because they rely on that magnetic shield for protection.
Precisely. During a weakened state, space weather, particles from solar flares would bombard Earth more directly. They could fry sensitive electronics. And then you have to think about the original navigator.
The animals, whales, sea turtles, migratory birds.
They all rely on the magnetic field to find their way across the globe. A chaotic or flipping field would present a huge challenge to their survival.
So to summarize our deep dive, the magnetic North Pole is profoundly unstable. It sped up dramatically, dragged itself towards Siberia, and forced global tech systems to update just to keep planes on course. And the source is the churning core, which remains totally chaotic. It could slow down more, or it could speed right back up.
And that continuous volatility just highlights the importance of monitoring. Just like navigators have to constantly check the field's performance, we have to keep reassessing our understanding of this planet. The molten core beneath the crust really holds the keys to our future navigation.
Here's a fascinating thought to mull over. Life on Earth has weathered lots of magnetic reversals over millions of years, right? But we have never experienced one when modern technology was present. Engineers would potentially have centuries to adapt to a drastically weakened field. So if a reversal truly began today, what modern infrastructure beyond just GPS satellites is most vulnerable to the slow erosion of our planet's unseen magnetic shield?
A truly mind-bending engineering challenge.
Indeed. Thank you for diving deep with us.
Don't forget to like and subscribe for the next episode on While We Were Distracted.